Hi, everyone. Welcome to the next video in our week 3 series on the central limit theorem for sample means. So we're going to suppose that X is a random variable with a distribution that we don't know. So X is a collection of raw data, and we don't know what that distribution looks like. We're going to use the subscript X to identify properties or summary statistics that belong to this data. So we're going to suppose that X or mu sub X, sorry, is the mean of X and sigma sub X is the standard deviation of X. So when we see mu sub X and sigma sub X, we're assuming that that is for raw data, a collection of individual data values. If we look at that same population and we draw random samples of size n, as that sample size n gets bigger, the random variable x bar, which is the set of the sample means from those samples, tends to be normally distributed. This is very powerful in statistics because if we're looking at a distribution of sample means, we know they are normal, even if the original raw data is not. And so that's going to allow us to use the normal distribution to describe a lot of systems that if we looked at the raw data are not normal, but those sample means are. So we would say that the sample mean has a normal distribution with a mean mu sub x, the same mean as the raw data, and a standard deviation sigma sub x divided by the square root of n. So the standard deviation for the distribution of sample means is the distribution or the standard deviation from the raw data divided by the square root of the sample size, meaning the distribution of sample means is going to be more squished together about that middle than the raw data. And that kind of makes sense. When we take an average, we're taking those data values on the edge of that sample and we're squishing them in towards the middle to find that midpoint. So it makes sense that if we're looking at a distribution of those averages, we would expect them to be more closely packed around the population mean than the raw data itself is. So the CLT, central limit theorem, says that if you keep drawing larger and larger samples and calculating their means, the sample means form their own normal distribution. And we call that distribution of sample means a sampling distribution. So a regular distribution is just raw data, individual values from a population. A sampling distribution is sample means of samples pulled from the population. The sampling distribution has the same mean as the original raw data. So mu sub x bar, the sampling distribution mean, is the same as the original mean. The sampling distribution has a standard deviation that's equal to the original distribution standard deviation divided by the square root of the sample size. And we call that value the standard error of the mean. So sigma sub x bar is the standard deviation of the sampling distribution, and it's also called the standard error of the mean. And we calculate it by taking the original standard deviation and dividing it by the square root of n. It's important to note that that n value is the size of a single sample, not the number of times we perform the experiment or the number of samples we collect. So we're going to collect lots and lots and lots of samples, but I'm only interested in the size of a single sample. If you are finding probability using table E, then you need to convert any sample means, x bars, into standardized z-scores. And to do that, you need to use the z-score formula, with the new mean and standard deviation. You'll notice that we have an x bar instead of an x. Mu x bar is equal to mu x, so that doesn't need to change. And in the bottom, where we would have a mu x bar, we've replaced it with what x bar is equal to, sigma sub x divided by square root of n. So this is just the regular z-score formula with these new formula substitutions for mean and standard deviation. If you are using a TI-84 or GeoGebra, you don't really need to worry about this z-score conversion because the calculators and the computers can find normal probability for any normal distribution. You don't need to convert to the standard normal. So you only really need to worry about this new z-score formula if you're working with the table in the book. So let's do an example really quick. Example 7.1 says an unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size n equals 25 are drawn randomly from the population. Find the probability that the sample mean is between 85 and 92. Find the value that is 2 standard deviations above the expected value, 90, of the sample mean. So let's go ahead and tackle A first. So A says find the probability the sample mean is between 85 and 92. So to start, I'm going to pick through that word problem and identify what we know. So first thing is they say an unknown distribution. This is our raw data. Those are those original X values. And the unknown means I don't know what that distribution looks like. I don't know if it's normal. I don't know if it's skewed. I don't know if it's bimodal. But I do know that it has a mean of 90. Mu sub x equals 90. And it has a standard deviation of 15. So sigma sub x is 15. And then I'm told I'm drawing samples of size n equals 25. The problem then says find the probability that a sample mean is between 85 and 92. So I know that I'm looking not at individual data, but at sample means. So between the samples of size 25 and the question that it asked about sample means, I know that I'm working with a sampling distribution. Which means I know a couple of things. I know that these are going to be normally distributed, right? My X bars should be normally distributed. I know that the mean for the sampling distribution is the same as the mean for the original data. So we know that that's going to be 90. And we know that the standard deviation for the sampling distribution is going to be the original standard deviation divided by the square root of n. So sigma x is 15, and the square root of n is going to be the square root of 25. I happen to know the square root of 25 is 5, and 15 divided by 5 is 3. Once I've made that list, I know I have a normal distribution. I know what my mean and standard deviation are. This looks exactly like the problems from chapter 6. We're finding the probability for a normal distribution, and I want to find the probability that I'm between 85 and 92. In between, the variable I'm now looking at is x bars instead of x's. So I need to make sure I'm using that appropriate notation. Sampling distribution, my variable is x bar. If I'm doing this on a TI, I know I'm calling normal CDF. If I'm doing it on GeoGebra, I'm going to have to do a normal call. But before I look at those function calls, let's do what we know we're supposed to do at the beginning and draw our picture. That is horribly messy, and I apologize. I'm going to label my axis x bar because we're distributing sample means. I know that peak is at 90. And I know when I go to make my hash marks, when I'm counting out those standard deviations, I'm counting by threes because the standard deviation is 3. And then I'm going to shade in the area of interest. So I'm looking from 85, which is right about here, just above 84, all the way up to 92, which is just below that 93. So we're interested in finding this shaded area here. On a TI-84, we know we call normal CDF. And normal CDF looks for 4 things: the lower bound of the shaded area, the upper bound, the mean, and the standard deviation. So for us, lower bound is 85, upper bound is 92, our mean is 90, and our standard deviation for our sampling distribution is 3. Remember that if you're on GeoGebra, you need to do normal minus normal. So you're going to have a normal function call for the upper bound. And remember that GeoGebra wants the mean and the standard deviation first, and then that upper boundary. And then you'll repeat mean, standard deviation, lower boundary. So let me pull up my TI-84. Having a little bit of computer issue here. Let's get rid of that. And I'm going to shift this somewhere we can see it. Let me erase some stuff here. It's a little better. Okay. So we're going to go second vars, normal CDF, and then I'm going to enter those 5 values. So 85, 92, 90, and 3. And we get 6997. In terms of our picture, that kind of makes sense. We can see from our picture down here that that blue shading is a decent chunk of that curve, so that we're getting a probability that's bigger than 0.5 makes sense. So that means if I'm pulling samples of size 25 from the population, there is a 69.97% chance that one of those samples is going to produce a sample mean between 85 and 92. Okay, so let's go ahead. I'm going to redraw some of that information that we had. We know, oops, let me get to the next screen here. For part B, we want to find the value that's 2 standard deviations above the expected value 90 for the sample mean. So let's write what we know about our sampling distribution down. So we know for sample means it's a normal distribution. We know that our mean is the same as the original data, 90. And we found that this was 15 over the square root of 25, raw data divided by the square root of the sample size, which worked out to 3. And they say, find the value that's 2 standard deviations above the expected value of 90. So we want to do x bar is equal to 90 plus 2 standard deviations. And we know that our standard deviation for the sampling distribution is 3. So 90 plus 2 times 3 is 90 plus 6, which is 96. And we saw that in the picture on the last slide when we drew our normal distribution in preparation for our probability calculation, that 2 standard deviations above the mean hash mark was labeled 96. Okay, so let's do another example. This one says in a recent study reported October 29th, 2012, not that recent, on the Flurry blog, the mean age of tablet users is 34 years. Suppose the standard deviation is 15 years. Take a sample size of n equals 100. What are the mean and standard deviation for the same, I think that should say sample mean ages of tablet users? What does the distribution look like? Find the probability that the sample mean age is more than 30, and find the 95th percentile for the sample mean age. So let's go ahead and start with part A. What is the mean and standard deviation for the sample mean ages of tablet users? So let's fix my typo. So a couple of things we're going to read through. We're going to identify what we're given. Mean age of tablet users is 34. So mu sub x is 34. And then the standard deviation is 15. So sigma sub x is 15. And then we know that we're going to be looking at samples of size 100. The fact that they gave me this tells me I'm likely looking at a sampling distribution. And then in part A, they're asking about mean and standard deviations for the sample mean ages. So those two things together tell me I'm looking at a sampling distribution. So for a sampling distribution, we know 3 things. We know it should be normally distributed. We know the mean for the sampling distribution is equal to the mean of the raw data. So that's going to be 34 years. And then we know the standard deviation for the sampling distribution is the standard deviation of the raw data divided by the square root of the sample size. So standard deviation is 15 years. And then we want to divide that by the square root of the sample size, which is 100. I know the square root of 100 is 10, and 15 divided by 10 is going to be 1.5 years. So the mean and standard deviation for our sampling distribution, or our sample mean ages, is 34 years and 1.5 years. So we're going to keep that in the back of our head as we move forward, 34 years and 1.5 years. B says, what does the distribution look like? And we now have that information. Sampling distribution mean is 34. Sampling distribution standard deviation is 1.5. And we know because it's a sampling distribution that it should be normal. We know that the mean in the middle is 34. And then we know that our standard deviation hash marks we're counting by 1.5. So 35.5, 37, 32.5, 31. Sorry, had a brain fart there. And I know that if I want to write that using our distribution notation, that x is a normal distribution with a mean of 34 and a standard deviation of 1.5. So all of that information is coming from the central limit theorem because we're looking at sample means instead of raw data. C says find the probability that the sample mean age is more than 30. The reported age of tablet users, oh, there's another typo, in this particular study. So let's write that information that we have. Sample mean, sampling distribution mean is 34. standard error of the mean is 1.5. And they say find the probability that x is greater than 30. And they specifically say the probability that the sample mean is greater than 30. So that's an x bar. And when we draw our picture, we're drawing that same picture from the last slide. The peak is in the middle at 34, and we're counting by 1.5. And then we're going to mark 30 on our axis. And 30 is a little bit less than 31, so probably right about here. And we want more than 30. That's a greater than problem, so we're shading to the right. I see a few things. First, that 30 is out past the 2 standard deviation path mark, and I've shaded in most of this curve. So I'm expecting a really big probability. So something greater than 95%. This is going to be pretty big. So on a TI-84, we want lower bound, upper bound, mean, and standard deviation. So for this one, our lower bound is 30. And our upper bound is infinity, so 1E99. Mean is 34. Sampling distribution standard deviation is 1.5. Or if you're on GeoGebra, or if you're using table E, GeoGebra and table E only find areas to the left. So we need to use the complement rule and do 1 minus that normal function call. And GeoGebra wants the mean, the standard deviation, and the upper bound. So for us, that's going to be 34, 1.5, and 30. So I'm going to pull up my TI-84 again. So second vars, go down to option 2. Our lower is 30, our upper is 1, and then second comma to pull up that E, and then 34 and 1.5. And my calculator gives us an answer of 0.9962. So a little bit bigger than 99%, which matches with what we drew in our picture, almost the entire curve. So based on the information that we have about this distribution of ages, we're expecting that there is a 99.62% chance that a sample mean age is more than 30 years. So a random sample of 100 people, there's a 99.6% chance that that sample average age is bigger than 30. And then the last question says, find the 95th percentile for the sample mean age to 1 decimal place. So again, we know for our sampling distribution, as we're looking at sample mean age, 34, and standard error of the mean is 1.5. And we know to find percentiles, they're giving us a percentage. They're saying P X bar less than whatever value we're looking for is equal to 0.95. We just need to figure out what that is. So first we're going to draw a picture. Here's our mean of 34. We want to mark off 95%. So this represents 95% of the curve. And we learned in one of our earlier videos that when we have the answer, we have the probability, and we want that boundary value, we use inverse norm. So to figure out that question mark, I'm going to do on my calculator inverse norm. And then the TIs ask me for 3 pieces of information. They ask me for the area to the left, our 95%, and then our mean and our standard deviation. If you're on GeoGebra, similar, inverse normal. And then GeoGebra wants the mean and standard deviation in front. So 34, 1.5, and then the area to the left. So I'm gonna, again, pull up my TI-84. And we find inverse norm in the same menu we find normal CDF, so second bars. And it's option 3. And then 0.95, 34, and 1.5. And so we get 36 point, and they said round to 1 decimal place, so that would round up to 5. So this area here is bounded by 36.5. So what that tells me is that if I'm looking at the distribution of sample mean ages, that I expect 95% of those sample mean ages to be less than 36.5 years old. Okay, so there's 2 more videos coming this week on how to tell when it's raw data versus sampling distribution, and then just some more work through examples. If you have any questions on anything you've seen, please contact me via email or text message. And then again, I have office hours on Thursday from 12 to 1 and 7 to 8. Not a lot of people taking advantage of those. So if you need to meet outside of those hours, send me an email and I can set up a Zoom session for you outside of those hours. I hope you're having a good week, and I'll see you in the next video.